So yeah, my talk today is on this topic of embeddedness of time-like maximal surfaces, or minimal surfaces, or zero mean curvature surfaces, whatever you want to call them. And everything I'm really going to cover today is contained in my paper, which is freely available on the archive. And I've also put the slides for this talk up on my web page, so you can find the slides to follow along. And finally, I put my email address here, and it's going to be here throughout the talk. So please write to me, is what I wanted to say. If you have any questions about the talk or about minimal surface theory more generally, if you just want to chat, you know, I'm always very, very happy to chat with people. Okay. So just to give you a very rough plan of my talk, I'm going to start off with a sort of very brief tour of the classical theory of minimal surfaces in Euclidean space. And then once I've done that, I'm going to move on to differential geometry in Minkowski space and the situation for maximal, i.e. minimal surfaces there. And really my focus is going to be on the so-called Cauchy problem for time-like maximal surfaces. And then these are sort of introductory parts of the talk. Then the main part of the talk, the final part of the talk, I'm going to present some new results. So the first result I'm going to present is the following theorem, which states that every smooth, properly immersed, time-like maximal surface in 1+2 Minkowski space is an embedded surface. So that means it doesn't have any self-intersections. And moreover is a smooth graph over all bounded subsets. And then the second theorem I'm going to present today is regarding the so-called singularity formation for time-like maximal surfaces. And I'm going to present that this singularity formation always involves a curvature blow-up, with that blow-up given in some precise sense. So that's the kind of overview of the talk, and there may be some terminology here you don't understand or you don't know. That's fine. It's now my job to go and explain everything. So I hope that these results will be made clear by the end of the talk. So to start off, sort of the classical theory of minimal surfaces in Euclidean space, and this is something that mathematicians have been studying for a long time. In fact, it was in 1760 that Lagrange first wrote down this equation, the sort of minimal surface equation, describing a surface in Euclidean space, which is parameterized in a graphical form, which extremizes the area functional. So that's what we now call a minimal surface. And minimal surfaces are nice, of course, because they describe sort of familiar soap films from everyday life. And although Lagrange wrote down this kind of nasty nonlinear PDE, he didn't actually write down any explicit solutions apart from the kind of trivial solutions, so sort of u equals 0. It's a trivial solution to this equation representing a planar surface. So for the first non-trivial solutions, we had to wait until 1776 when Meissner came along, and he identified the surfaces of minimal surfaces as being surfaces of vanishing mean curvature. Okay, so he gave a geometric interpretation of this equation, and then using geometric techniques, he was then able to cook up some non-trivial examples, the famous catenoid and helicoid, which are written here. And of course, well, neither of these surfaces can be written globally as a graph. They can't be globally parameterized as a graph, but over any sort of local graphical patch there, you solve Lagrange's minimal surface equation. So that was sort of 250 years ago, and over the last 250 years, so many more exciting examples of minimal surfaces have been found. So I've just put a couple of famous examples up on the slide here, but I mean, there's really a plethora of interesting examples out there of these surfaces, and we're still discovering them to this day. So it's been a sort of rich topic of research. And not only have we constructed many nice examples of minimal surfaces, we sort of now have all these nice theorems about them. So in particular, I want to focus on two theorems today for minimal surfaces, the so-called rigidity theorems. So the first theorem is due to Bernstein, and Bernstein's theorem says that any smooth complete minimal surface in Euclidean space, which is a graphical surface, so it can be parameterized globally as a graph, i.e. in this form, well, it must be a plane, okay? So the only possible such graphical surfaces are the trivial planar solutions. And this has a nice interpretation as a kind of PDE result. It just says that there are no non-trivial global solutions to Lagrange's minimal surface equation. And the second sort of very famous theorem I want to mention is due to Fujimoto. And this theorem is actually a generalization of Bernstein's theorem. And it states that if sigma is a complete minimal surface in Euclidean space, and n is its unit normal vector, so that's a unit vector by definition, so it defines a map from the surface into the unit sphere. Well, the image of that map can fall into one of two classes. Either it can be a single point, in which case it's clear to see that your surface has to be a planar solution, or its image admits at most 4 points in the unit sphere. So this is a really beautiful theorem. You can sort of see that it's a generalization of this result. And it's kind of amazing that we have all these sort of examples, sort of intricate examples of complete minimal surfaces, which I sort of showed on the last slide. But all of these surfaces have a unit normal, which admits at most 4 points in the sphere. So that's all I want to say about this theory of minimal surfaces in Euclidean space. Now let me move on to Minkowski space. So Minkowski space, well, it's like Euclidean space, except we have this, our Euclidean inner product is now replaced with this Minkowski inner product. And of course, the defining feature of this inner product is that vectors can have positive or negative or zero length. So we say a vector is time-like if it has negative length, space-like if it has positive length, and null if it has zero length. And then we can sort of draw these nice pictures where at any point P in Minkowski space, you draw a little cone, the light cone, and that consists of all the null vectors. And then the interior of the light cone is all the time-like vectors, and the exterior of the light cone is all the space-like vectors. So that's the definition of Minkowski space, and that's how we classify vectors in Minkowski space. But we're really interested in surfaces in Minkowski space, immersed surfaces. And we can also classify surfaces as space-like and time-like. So we say that if U is a two-dimensional surface and phi is a smooth immersion of that surface into Minkowski space, we define this bilinear form. This is the induced metric. And we say that phi is a time-like immersion, so the immersion is time-like, if the determinant of this form is negative. So in other words, if the induced metric is a Lorentzian metric on the surface. And this is a kind of algebraic condition, but there's an equivalent geometric criterion for sort of, which helps to visualize what a time-like surface should look like. And I've kind of drawn it, sketched it here. So you can show that an immersion is time-like if and only if there exists a pair of non-vanishing vector fields, call them n plus and n minus, which live on U, such that under the immersion, they push forward to give a pair of null vectors, which are spanning the tangent plane to the surface. So this shows you that the time-like surfaces are characterized by, they have tangent planes, which they always intersect the light cone along two distinct linearly independent directions. So that they have kind of tangent planes which are always inclined by less than 45 degrees. So that's how you can visualize what a time-like immersion looks like. And it's kind of clear that this notion of time-likeness, it places some sort of constraints on the possible shape of a time-like surface. And that's the content of the following lemma, which is a sort of a simple application of sort of Morse theory, which says that time-like surfaces can be kind of visualized as flows of curves. So the lemma says that if U is a connected surface and phi is a smooth time-like immersion of that surface into Minkowski space, which in addition satisfies this kind of simple topological notion of properness. So you can recall that a map is proper if the pre-image of a compact set is compact. So if you have a proper immersion, then it turns out that there exists a smooth diffeomorphism between your original surface U and either a cylinder or a plane, such that after applying this diffeomorphism, one's map takes the following form, where so the map is kind of, the surface is parametrized by the Minkowskian time coordinate t and a flow of immersed planar curves gamma with t. So you can kind of visualize this lemma in sort of layman's terms. This lemma says that if you look at the class of properly immersed time-like surfaces, well, then you can only have two possible flavors. You can either have a sort of cylindrical surface, which looks like this. It's a flow of closed curves, or you can have a kind of planar surface, which looks like this, and that's a flow of non-compact curves. So maybe I'll just pause here in case anyone has any questions they would like to raise before going on.
Any questions?
Yes. Hi, Adam. This is Jens.
Hi, yes.
The second picture on the right, I just made it. The second you put on the first slide, I was late, sorry. But I from the very first slide, I could follow. The second picture, you have a self-intersection of that curve?
Yes.
Okay, I just wanted to ask. Okay.
No, I wanted the picture to make that clear that that this doesn't rule out self-intersections. You can certainly have self-intersecting time-like, properly immersed time-like surfaces.
Good. Yeah.
Okay.
Thank you.
Great. Thanks for the great question. So now I will proceed. Okay, so I've kind of told you we now should be happy with the notion of a time-like immersion, a time-like immersed surface. So let's define what it means to be a maximal surface, i.e. minimal surface. So we say that a smooth time-like immersion is maximal if if its mean curvature vector vanishes. And that corresponds to the following sort of geometric PDE. And in order to make this a kind of well-posed equation to work with, one has to fix coordinates. So you can choose many different ways to fix coordinates. You can parameterize surfaces in many different ways. If you have a surface parameterized as a graph, so in this graphical parameterization, then the mean curvature zero condition reduces to the so-called Born-Infeld equation here, which looks very much like a kind of hyperbolic analog of the Lagrange's minimal surface equation. But if you can be sort of even more clever and you can construct so-called isothermal coordinates on the surface, I'm going to call them S and T, and that's coordinates for which the induced metric takes this particularly nice diagonalized form, then your mean curvature equation will reduce to just a linear wave equation. So the choice of coordinates, choice of parameterization of your surface really dictates the PDE you end up working with. But in any case, sort of the thing to bear in mind is in any case, we end up with a wave type equation, okay? Because we're dealing with time-like surfaces, so that means that this form G is a kind of signature minus plus. So in any case, we end up with a kind of hyperbolic wave type equation. And as such, I'd like to claim here that a kind of natural problem to go about studying the time-like maximal surfaces is the Cauchy problem, or otherwise known as the initial value problem. So what is the Cauchy problem for time-like maximal surfaces? Well, it is the following. The Cauchy problem states, given a smooth immersed curve C in the initial plane t equals 0, and a smooth time-like vector field V along C, the Cauchy problem is now to find a smooth immersed time-like maximal surface sigma, which intersects C and is tangent to V along C. So I've drawn that sort of schematically here. So for the Cauchy problem, you give me some initial curve C in the plane, and we have a wave equation, so I should also ask you to dictate for me some velocity. So you also give me a vector field along that curve C. And then my job to solve the Cauchy problem is to find you a time-like surface which satisfies the PDE, i.e. is a maximal surface, which intersects C and is tangent to D along C. So this is a kind of natural geometric evolution problem. And for any geometric evolution problem, you really want a notion of global solution. Okay, what should be a global solution to this problem? Well, I claim that a good notion of global solution is a proper immersion, okay, a properly immersed surface. And we can see this as a good, nice notion of global solution because of the Morse lemma from a few slides back, which told us that the properly immersed surfaces are sort of global flows of immersed planar curves. So that sort of gives some credence to this idea that that's a good notion of a global solution. Okay, so that was some kind of abstract talk. So let's have a simple example. So let's suppose that we're playing the Cauchy problem, and you have given me as initial data a curve C, which is just a circle in the initial plane. And you chose a very simple velocity field along that curve. You just chose the one which points up in the, I'd write this as the t direction, x0, t. Well, it turns out for this particularly simple choice of initial data, I can cook up an explicit solution of the Cauchy problem. And here it is. And this is a surface which I've plotted here on the right. It looks like a cosine profile, which has been rotated by 360 degrees around the x0 plane. And this is it's an immersed surface everywhere except for at these discrete singular points, which occur periodically, where the map fails to give an immersion. And you can go away and check as an exercise that this is at least away from the singular points. This is a time-like immersion, and moreover, it's a time-like immersion with vanishing mean curvature. So it's a time-like maximal immersion. And from the point of view of the Cauchy problem, we have a sort of evolution here of curves, where my initial curve, which you posed the initial data, was this circle here in the initial plane. And then I solved the Cauchy problem, and as time progresses, I trace out a kind of flow of immersed planar curves, where the curves are all circles with radiuses shrinking with time, until eventually, at some time, the curves shrink to a point. And I have a flow of round circles which collapse to a point in finite time. So the point of this example was to illustrate a case of singularity formation for a nonlinear evolution problem, for this Cauchy problem of time-like maximal surfaces. So here we have a local solution to the Cauchy problem, which does not extend to a global solution, but rather collapses to a finite time singularity. Before I sort of proceed, you're probably justified in saying, well, where did this come from? You just chose some initial data and then cooked up a solution to the equations sort of by magic. Well, this is actually a particular example of a more general technique, something I call the method of isothermal gauge, solving the equations in the isothermal gauge. It's sort of really the twin of the Weierstrass representation formula for minimal surfaces. I don't want to go into this construction today because I think lots of people know this construction. They know it by different names. I just want to say something about sort of what it is. Well, it's a general trick for cooking up solutions to this system of equations. So cooking up solutions to the wave equation, which also satisfy these conformal conditions, i.e. Such that these are kind of like isothermal coordinate conditions. And it turns out to be quite simple to sort of cook up solutions to this system of equations. And that will give you an example of a time-like maximal surface, provided the map phi is an immersion. And this is a kind of key point. In general, the map which you construct solving these equations will not be an immersion, and thus the surface it gives you will be a singular time-like maximal surface. As seen here, we have singularities at points where the map fails to give an immersion. So from the point of view of the Cauchy problem, which is sort of the theme of my talk today, we can use this trick in general to construct local solutions to the Cauchy problem. And that's a very useful tool for sort of explicit analysis. But in general, those local solutions do not extend to give global solutions to the Cauchy problem. Because in general, this map fails to give an immersion. And when it fails to give an immersion, you can have formation of singularities. Okay, and then I wanted to say that this is a really nice example, this shrinking circle. It turns out to be a special case of a nice theorem of Bellatini, Hoppe, Navaga, and Orlandi. So they showed that if you have an initial curve C, which is a smooth, closed, convex, centrally symmetric curve, so this is some technical symmetry assumption, and again you choose this nice simple form of the initial velocity along C, then the Cauchy evolution of that initial data to a time-like maximal surface will consist of a family of smooth, closed, convex curves which shrink to a point singularity in finite time. So this behavior we see here for the circle actually generalizes to a larger class of curves satisfying some symmetry assumption. But it should be noted that this, although it's a very elegant situation, it turns out not to be the generic singularity formation. So if one starts with some initial data and evolves that data and then runs into a singularity, generically the singularity will not look something like this, like a collapse. Generically, it will look generally something like a sort of pinch singularity. And we can see that by working with the isothermal gauge. It can be shown that generically, for singular time-like maximal surfaces constructed by this special method of isothermal gauge, the sort of singularity formation looks like a swallowtail, which is drawn here. And in this picture, typically what happens is that at the first time of singularity, the limiting curve is actually a C1 curve. So the sort of first time, this is a kind of plot of the singularity formation with the sort of curves evolve with time as I move to the right. And the sort of first time of singularity happens around here. And there the limit curve is actually still a C1 curve before it then splits off into a sort of pair of cusps. And I'm not going to go into the details of this analysis, but there's very nice treatment of this in Eggers and Hoppe, and also in Wien and Tian. So that tells you a little bit about what singularities look like when they do form for these equations. But you're well justified in asking, how regularly do singularities form? So given some initial data, when can I expect my initial data to form into a singularity? Is this something which happens very often or very rarely? In which cases? And it turns out, so I've put here that time-like maximal surfaces, they like to form singularities. So it happens quite often. And that's nicely illustrated by the following theorem. And I think it's fair to say this is an observation that was noted independently by a number of different authors, by Pronko, Razumov, and Soloviev in the 80s, and by Hoppe in the 90s, and then later by Wien and Tian in 2013. And perhaps these guys gave the first sort of rigorous proof of this statement. But the theorem states, in any case, that there exists no smooth, proper time-like maximal immersion of the cylinder into Minkowski space. So, in other words, there are no global solutions to the equations in the case of a spatially compact evolving curve. So if you give me any, it follows from this result that if you give me any initial curve C, which is a closed curve, and some time-like vector field along that closed curve C, and then you ask for a solution to the Cauchy problem, that solution has to degenerate into a singularity in finite time. And the way you can see that is that, well, if it didn't form a singularity, then it would eventually evolve to give a global solution to the equations, which would contradict this theorem about non-existence of global solutions. Recall again that I say the proper immersion is a kind of global solution. So that in some sense clears up the picture for evolutions of compact curves, closed curves. But you can ask, what about the case of evolutions of spatially non-compact curves? So if I give you a non-compact initial curve and some velocity field along that curve, and I look to evolve this to a time-like maximal surface, what can be said? In which cases do I expect singularity, and in which cases do I expect global solutions to the equations? And well, that's the content of the following theorem. So theorem 1 states that let phi be a smooth, proper, time-like maximal immersion of the plane into Minkowski space. So here we're considering global solutions of the equations in the case of an evolving non-compact curve, i.e. an immersed plane. Well, then first off, phi has to be an embedding. So in other words, the surface cannot self-intersect itself. And second, I can say even stronger than this, for every sort of generalization of this, strengthening, for every compact subset K of the image of phi, of the immersed surface, there is a time-like plane P such that K is a smooth graph over P. So in some senses, all of the global solutions are embedded surfaces, and even more than that, they're actually graphs of the compact subsets. And you might like to think of this theorem as being a bit like an upside-down Bernstein's theorem. You can recall that Bernstein's theorem said that there are no sort of interesting global solutions of minimal surfaces in Euclidean space, which are not graphs. Which are graphs. Sorry, all of the interesting examples of minimal surfaces are sort of not graphs. Well, this result here says that all of the interesting global examples in Minkowski space, well, they are graphs, okay? Or at least they are graphs modulo this technical restriction to compact subsets, which I will get to in a minute. So that's one nice way of picturing this theorem. And you may also recall I mentioned Fujimoto's theorem about the unit normal for minimal surfaces in R3. It turns out we can also sort of interpret theorem 1 as a statement about the unit normal. So it can be sort of shown to follow quite easily from theorem 1 that if sigma is a smooth, properly immersed time-like maximal surface in Minkowski space, and n is its unit normal vector, it's a space-like vector, then the image of n is contained in a closed hemi-hyperboloid. Okay, so you should recall that in Minkowski space, the unit sphere is no longer a sphere, it's now a hyperboloid. So that's a kind of nice geometric consequence of this theorem. But the consequence that I really want to focus on today is regards the Cauchy problem. So it follows from this theorem that if I take any self-intersecting curve C and any time-like vector field V along C, and I look to evolve this initial data, well, then the Cauchy evolution of that data must form a finite time singularity at some point in either the future or the past. And the way you can see that this follows from theorem 1 is, well, by contradiction, if it didn't form a singularity, then I would have some global solution to the equations, which would give me a properly immersed time-like maximal surface, which had a self-intersection, but that would contradict the first part of this theorem here. So we must have some singularity formation. And in fact, that just used the first part of this theorem. If you use the second part of the theorem, you can get an even stronger criterion on the initial curve. You can replace self-intersecting curve with any curve with a sort of non-graphical compact subset. But for sort of illustrative purposes, let's just think about self-intersecting curves. So I'm actually going to give a proof of this theorem because I think it's a really nice quick proof which can be easily given. But before I do that, I should just make a couple of notes about the theorem. So the first question you might ask is, well, this theorem tells me something about all global solutions to the equations must have the following form, but are there any actual global solutions with this form? I mean, are there any interesting solutions to the equations? And it turns out the answer is yes. In fact, within the sort of smooth graphical regime, there are many examples of global solutions to the equations. And one way to see this is to use the method of isothermal gauge. So here's an example of evolution by isothermal gauge. If I have any planar curve C, which is actually a smooth proper graph, so it's a graphical curve, and then I define this evolution of C by isothermal gauge, this is kind of looks suspiciously like D'Alembert's formula, well then one can show that this gives an example of a smooth, properly immersed time-like maximal surface, which is a graph, globally a graph. So there's lots of examples, and you could kind of think about this as reflecting sort of stability of the planar solution, which sort of stability of trivial solutions is a common theme in nonlinear wave equations. And then the second note before I move on, it regards this restriction to compact subsets. So you should ask, is this a necessary restriction to compact subsets? Or are in fact all of the global solutions just graphs globally, right? Or do we actually need this restriction? It turns out this is a necessary restriction which can't be relaxed. And the way to see that, we can construct an example. Again, we take this formula phi, but for the curve C here in phi, we take the following curve parameterized by arc length, which I've kind of sketched here. And so this curve contains a section of the x2 axis, and then it asymptotes to a line parallel to the x2 axis on the other side. And the key point to note about this curve is that it cannot be parameterized globally as a graph. Okay? It admits no global graphical parameterization. However, if I take any compact subset of this curve, so if I cut off this curve away from some compact subset, then I can always find a line over which the curve can be parameterized as a graph. So this is a curve for which for every compact subset I can find a graphical parameterization, but no such parameterization exists globally. And if you generate a maximal surface by this method, starting with this curve, it can be shown, it's an exercise, that the resulting surface is a smooth, properly embedded time-like maximal surface, which cannot be written globally as a graph, but for which every compact subset can be parameterized globally as a graph. So in agreement with this second part of the theorem. Okay, so I'm now going to give the proof of this theorem. Well, I'm going to sketch the proof. So to give us a sketch proof of this theorem, we let phi be a smooth, proper time-like maximal immersion of the plane into Minkowski space, i.e. a global solution of the equations. And we want to show that phi is an embedding and that its image is a graph over compact subsets. So the proof can be broken down into roughly 3 steps. So the first step is to construct a coordinate change on the domain such that after a change of coordinates, the coordinate directions, n plus and n minus, are actually null vectors on the image. In other words, you construct a global system of isothermal coordinates on the surface. So I've sort of illustrated this schematically here, where we have a parameterization now where the coordinate lines downstairs map to null lines upstairs. And crucially, you note that this parameterization is defined on the entire plane, the entire of the plane, not just some subset of the plane. So this shows that we construct a smooth conformal equivalence between our initial surface and the Minkowski plane. And actually, we give a proof of this in the paper, but it turns out that this was a fact which was proved by Tilla Milner in 1985. So this has been established by her quite a while ago. And should we note that this is actually a really non-trivial fact, and I really want to kind of emphasize this point. The reason this is non-trivial is that it turns out there actually exist infinitely many possible conformal structures of simply connected Lorentzian surfaces. So out of infinitely many possible choices for the conformal structure, it's kind of amazing that all of the maximal surfaces have this particular conformal structure of the plane. So this is a really remarkable result. And I want to draw your attention today to the fact that actually this key result is really central to the proof of Theorem 1. And I hope that it will become clear in step 2 why this is so central. So step 2 of the theorem is to show that as a consequence of step 1, we have that the null directions to the surface, n plus and n minus, are linearly independent between all points of the surface. So every 2 points of the surface are somehow speaking to one another and dictating linearly independence. So I'm now going to show you how we prove step 2 from step 1. So the way to prove step 2 from step 1 is to argue by contradiction. Suppose that I can find 2 points P and Q, here's P and here's Q, such that the outgoing null direction n plus at P and the incoming null direction n minus at Q are linearly dependent. That's what this little symbol is supposed to mean, linearly dependent. And suppose we have a situation where these guys are linearly dependent. Well, now, we have a maximal surface parametrized conformally, okay? So that means that my immersion satisfies the wave equation, okay? D squared phi by d plus d minus is 0. And we can break down the wave equation into a pair of transport equations. So d plus of n minus is d minus of n plus is 0. That's just another way of writing this. And that reveals a really key property of timelike maximal surfaces, which is that the outgoing null directions are always constant along incoming null lines, whereas the incoming null directions are always constant along the outgoing null lines. So by this property, it means I can always then find a point R. Okay, so there exists a point R, which I've written here, such that n plus at P is equal to n plus at R, and n minus at Q is equal to n minus at R, okay, by parallel transport. But then I've assumed that n plus at P and n minus at Q are linearly independent. But that shows that n plus at R and n minus at R are linearly dependent. And so that gives a contradiction. So we've proved step 2. And I really want to draw your attention to the fact that step 2, the proof of step 2, it relies really crucially on step 1. It relies a lot on this particular conformal structure. If we didn't have the conformal structure of the plane, we had one of the other infinitely many possible conformal structures, then I wouldn't always be able to find this point R, which connects P and Q in this manner. So this conformal structure really plays a key role in making sure that 2 points on the surface are always talking to one another. And then the final step of the theorem, and this is the one I'm really just going to sketch, and I'm going to leave it as an exercise, is to say, well, once we've proved step 2, let's now forget about these null coordinates, and let's change coordinates back to the so-called Morse coordinates. So I view the surface now as a flow of curves. And I'm going to define E to be the unit tangent of the evolving curves, the evolving planar cross-section. So just to draw this in a picture, I kind of now view sigma as a flow of curves, gamma, so for every t I have an immersed curve gamma, and I define E to be the spatial tangent to that curve. And now E is a unit vector, so it lies in a circle, S1. The image of E is a subset of the circle, S1. And I claim that as a consequence of step 2, I must have that the image of E is a strict subset of a closed semicircle. So this is the step I'm going to leave as a sort of an exercise, but let me just sort of roughly give you an idea of how you should go about showing this. Try arguing by a contradiction. If the image of E is not a strict subset of a closed semicircle, in other words, the image of E contains a closed semicircle, in other words, I can find at some point in its journey, E makes a rotation of 180 degrees, okay? So suppose that your unit tangent rotates by 180 degrees. Then you have a collection of time-like planes along this unit, which are kind of moving, and they're rotating about the x-0 axis by 180 degrees. And you have to show that if that's the case, then I can always find 2 points P and Q, such that the one null vector at P becomes linearly dependent with the other null vector at Q, which contradicts step 2. So there's a kind of geometric argument going on here, which is perhaps in some sense the core of the proof, but I leave that as an exercise. And once you have this result that the image of the unit tangent is contained in the spatial unit tangent is contained in a closed semicircle, well, you can kind of see that then the evolving curves can never backtrack and self-intersect. It's actually a kind of then it follows from some simple differential geometry. Again, I leave this as an exercise to show that then your initial immersion must be an embedding, and moreover, all the compact subsets are graphical. So that was quite a lot. Before I move on to give the final part of the talk, I stop again for questions.
Any questions? I have some questions which I'll reserve for the end.
Okay, great. Thanks, Rukmini. Okay, so that was the proof of theorem 1. And for the rest of the talk, I want to return to our Cauchy problem, and I want to look at look again at the Cauchy problem. So recall that as a consequence of theorem 1, we know that for any self-intersecting initial curve and any initial velocity along that initial curve, then the Cauchy evolution of that data to a time-like maximal surface must form a finite time singularity in either the future or the past. Okay, so this is a consequence of theorem 1, and the way we observe this consequence is by contradiction. So if such an evolution did not form a singularity, then we would have a global solution to the equations, which would be a self-intersecting, properly immersed time-like maximal surface, which contradicts theorem 1. But this doesn't actually tell us anything about the nature of singularity formation, right? It tells us that a singularity must be forming, but it doesn't tell us anything about what's actually going on at the formation of singularity. And from sort of first principles, there are two possible things that can happen at a singularity. So either the surface could fail to remain time-like you could pick up null points on your surface, or the surface can fail to remain smooth. Okay, so these are the two sort of, from first principles, the two things that could go wrong. And it's not a priori obvious that one implies two or vice versa. But in fact, it turns out to be quite well known that the case 1 always occurs in the case of the maximal surface equations. Okay, so it can be shown that you can't have a sort of loss of smoothness without loss of time-likeness. So singularity formation always involves the formation of loss of time-likeness, so null points in some way. But that doesn't tell us that necessarily we have to lose smoothness. Okay, so it could be a situation that we gain sort of null points, but we remain smooth. Okay, so these guys show that loss of time-likeness always happens. Let me be a bit more precise about what I mean by that. So they can show that at the first time of singularity, one always, call it T star, one always has the following picture, which I call loss of time-likeness. At the first time of singularity, I can always parameterize my surface in the following form, which I've drawn here, where our domain is a little box of height epsilon and base I call 2 delta. So we're kind of working locally in a vicinity of the singularity. And we can always have a parameterization which is kind of this kind of Morse form where one of my coordinates is the time t, and then we have a flow of curves, gamma with t. And I can always set up my parameterization to satisfy this orthogonality condition. So the velocity d gamma by dt is orthogonal to the unit tangent d gamma by ds along this curve s equals 0, and such that then this velocity d gamma by dt is converging up to 1, or to the speed of light as I approach the singular time along this curve. So this is a kind of what we can always, it turns out, parameterize the surface in a neighborhood of the singularity in the following form. And in this picture, we have a smooth time-like immersion on everywhere away from the singular time t, but we don't know anything about what happens at the singular time. And as we approach the singular time, the unit normal vector to the time-like surface in this picture turns out to be blowing up as a consequence of this condition in a kind of L infinity norm. And so one can easily show that in the special case that phi is a C1 immersion, so in the special case that this limit curve here is actually a C1 curve, and I have a C1 immersion up to the curve, then my surface is actually becomes null at this point. This has to be a null point. But in general, I don't have to know that this limit curve is C1. It could be a collapse. It doesn't make sense necessarily to speak of the surface being null at the singular time if there's a sufficient loss of regularity. But I kind of call this point a kind of null point in inverted commas anyway. So this is a picture which we always know happens at a singular time, and this picture could be simply due to a surface becoming null but remaining smooth, for example. It doesn't tell us immediately that there's a loss of regularity. And that's the content of my second theorem, which says that if phi is a time-like immersion of the above form, which we know we can always achieve in the case of singularity formation for the maximal surface, and suppose in addition that all I have is some uniform pointwise bound on the mean curvature, okay? So in the case of the maximal surface, the mean curvature is 0, so this certainly holds. Well, then I can deduce that there must necessarily be a blow-up of curvature, where by curvature I mean the curvature of the evolving planar curve gamma, k, that's a kind of scalar curvature, and the blow-up is in an L1 sense. So as I move along this time-like curve, proceeding toward the singularity, the curvature of these planar curves is blowing up pointwise, and the rate of blow-up is sort of faster, at least as fast as L1 along the curve. And in particular, a consequence of this result is that the map phi cannot be C2. Okay, so you cannot have a situation where you lose time-likeness, you get a null point, but the surface remains smooth. Okay, because there must be a loss of regularity, and that loss of regularity has to happen at the level of C2. So that's the second theorem. I'll maybe just make one quick technical remark about this theorem for the kind of experts in the field, which is that I did mention earlier that there's a kind of good understanding already of the sort of singularity formation in the generic case of the swallowtail singularity. And that uses a kind of analysis of this evolution by isothermal gauge. I think I should stress that I think that the key point about this theorem is that it's more general. It doesn't rely, the proof of this theorem doesn't rely on any explicit representation formula for the solution. And you can see that as a more general statement, not just for surfaces of vanishing mean curvature, but also surfaces of bounded mean curvature, where in the case of the vanishing mean curvature, we have some explicit representation formula, the D'Alembert formula, but for other cases, we don't necessarily have that. And so as such, this theorem is about the sort of general case of singularity formation rather than the generic case. So it may be already known that in the generic case, we always have a loss of a curvature blow up, but that doesn't cover the general case. This theorem covers the general case. Okay, so that's my second theorem, and now this is going to be my last slide. So I'm just going to wrap things up. So wrapping up, we've shown that every smooth, properly immersed time-like maximal surface in Minkowski space is an embedded surface, and it's a smooth graph over all bounded subsets. We've also looked at singularity formation for such a surface. So then if you then leave the class of smooth, properly immersed time-like maximal surfaces, well, you can't have a situation where you form a singularity as a result of a null point, but remain smooth. So singularity formation necessitates that we have a loss of regularity at the level of C2 regularity. So that was theorem 2. But the evolution might still be C1. And I think this is just a point that I thought would be quite nice to leave on. We know, I sort of mentioned earlier, we know that generically, the first time of singularity, the limit curve is C1. So it's natural to ask questions about whether we can continue the evolution in a C1 manner. And this is actually something that I really don't know very much about. I think there's lots of open questions, interesting open questions here. Well, I'll just mention a couple of sort of fun examples which I've cooked up, which are here. So here are some kind of fun examples, and I made these using the famous evolution by isothermal gauge. So I'm not claiming that there's anything canonical about these examples. But these are examples of C1 properly embedded surfaces, properly embedded surfaces, which are smooth time-like maximal surfaces away from some null set. So in the first case here, I have a C1 surface, which is a smooth time-like maximal surface away from some pair of null lines, one going to the future and one going to the past. And this surface is kind of interesting because it contains a compact subset, which is not a graph, cannot be parameterized as a graph. So that is, we see we've now left this regime of the smooth solutions have to be graphs over compact subsets. And this second example is now a C1 surface, which is a smooth time-like maximal surface, away from only a sort of periodic lattice of discrete null points. Okay, so it's a C1 surface and it's a smooth time-like maximal surface everywhere except for these null points, where the surface becomes null, and the curvature necessarily blows up by the previous theorem. And this example contains, I take a compact subset of this surface. It turns out it gives me I can parameterize as a continuous graph, but not as a C1 graph. So there's some interesting kind of borderline behavior going on here, where again, we've left this regime and now we just have some discrete null points. But I should say that I have these kind of fun toy examples. I don't have any examples of C1 properly immersed surfaces which are self-intersecting and are time-like maximal surfaces away from some null set. So I can't cook up sort of self-intersecting surfaces by this trick, and there's a good reason for that, and that is a theorem which is in the paper, but I don't want to get into that now. I should say that this is just really some play, really. I think that this is a picture which is still not very well understood, and certainly there are lots of interesting questions to be asked. Okay, so I'll leave it there. Thank you very much.
Thank you, Adam, for this wonderful talk. Are there any questions?
Yeah, I'm just rushing to ask some question, Adam. The last in the last slide, you have can you say a little bit more about the parameterization? You have formulas for these two pictures. No,
yeah.
no, not this one. The next one, where you said the examples.
These
the two. These two. You have. I mean, some formulas like x in terms of two parameters for x0, x1, and x2 in the two examples.
So I'll write this down for you. So it's the same. Again, this can be found in the paper, but it's the same. No, it's not a very good pen. It's the same formula as the one that I wrote down earlier, where I talked about existence of graphical and non-graphical maximal surfaces. So if you have a formula, can you see this, Jens?
Wait a minute. Yeah. Mm-hmm.
So this is a formula, and if I take, and here C should be it should be a planar curve, so a curve in the plane, and it should be parameterized by arc length.
Mm-hmm.
And in such a case, this is just an evolution by isothermal gauge. If you have such a case, this will always give you a time-like maximal surface wherever it is an immersion. But in general,
and what? Yeah, in the two examples, what is C?
Yeah. So the first example, C is the following curve. So I have. I have something that looks a bit like, I hope this is clear. I have a curve which is, it contains two sections of straight line, and those are parallel lines. So take two parallel lines in the plane, so a half line, so they go up to infinity in either way, and then join them at the base by some some smooth manner, such that your kind of your curvature is positive. So you're just going from one to the other. Take that for your first case, you'll get this surface.
Yeah, thank you. And the second one, that's the one I'm mostly interested in. Yeah.
So the second one, you just take a kind of a periodic, periodically repeating curve, which looks like this. And it has to be periodically repeating, and it's a graph, a continuous graph, okay? But it has to be such that at these points here, the tangent is orthogonal to the x-axis. So the derivative, if you write this as a function, if you write y equals u of x, if you write this as y equals u of x, then u prime of x becomes infinite at these points.
Okay, thank you.
And so that's why this is a continuous graph, but not a C1 graph. And take any curve of this form, and you can cook up a surface as I put it on the
Thank you.
Any other questions, comments? I have a couple of questions. If nobody has, are there any questions? So I have a couple of quick questions. One is, you said the only generic, did you say that the only generic singularities are the swallowtail ones, or there could be other generic singularities?
Well, no, there are certainly other singularities, but the generic singularities,
the only generic ones are the swallowtails.
Yeah,
Okay.
the generic case is the swallowtail.
Okay.
I mean, the way you can see this is by, I don't know how familiar you are with this, what I call the isothermal gauge picture. But there you have a sort of explicit representation formula for these, and then they fail to give immersion.
Right.
You can look at a sort of the first time at which you hit you fail to be in immersion, and then you can do a Taylor series about that time.
Okay. Because
you have an explicit map that you're working with. And then you can say that, I think the first term in the Taylor series is maybe always vanishing, but then there's one term which is generically non-vanishing. That's the kind of first generically non-vanishing term in this Taylor series. And if that term is non-vanishing, then you can explicitly see, well, I can't remember exactly how many terms you need to be non-vanishing to get the precise swallowtail. Jens will be better equipped to answer that question. But I think this is really nicely treated in Jens's paper with Jens Eggers and also Wien and Tian. So maybe we can talk.
I'll take a look at those papers. And my second question is, this reminds me of this paper by Barbishov and Chernikov, in which they do this Born-Infeld solitons. And the C of S plus T and S minus T, they evolve it in time. Think of T as the time and evolve it, and the two solitons just pass through each other without changing shape.
Yeah.
So does that help at all? That kind of picture, does it help at all in this? And I think what you are calling the isothermal gauge is what they call the hodographic transformation.
Yeah.
Probably. Yeah. So.
Yeah, I mean, I never fully understood. Maybe I didn't take the time to properly go through their work. I think because I work in this, for me, the isothermal gauge, once you have that, it's so natural to work with that you don't really want to go and have another method. But I think that they are. I mean, I'm not quite sure how it works, but I think that they are roughly the same thing, this holographic transform and the isothermal, I expect. And certainly for example, for this formula again.
Right. I mean, if you write cosine of S plus T, can you, I can't see it. Let me try to see it.
Oh, can you not see what I'm putting on the screen here?
Yeah. Oh, okay. I saw C of S plus T and C of S minus T, right?
Yeah. So this,
Yeah.
in the case that C is a graphical curve parameterized
Right.
by arc length, this will give you a global solution, and it will have that nice property that you have. I mean, because it's just like the situation for a linear wave equation where waves.
Yeah.
We have
Like wave packets going through each other without changing their shape.
Yeah, exactly.
Okay.
But
Okay,
yeah,
thanks a lot. Are there any other questions, comments? Yeah, tell me.
I was going to say, I know that you and Rahul are sort of experts in this.
No, we are not experts.
Yeah, I think there's lots of. It'd be very interesting to see how these two pictures interplay.
Yeah, I mean, it might be a useful technique for this time-like maximal surfaces. We call them Born-Infeld solitons.
Yeah.
Yeah. So, I guess. Yeah. Any other questions or comments?
Not a question, but a small comment with regard to the last question asked. So there is this very good, wonderful original work of Barbashov and Chernikov,
right?
Which is always forgotten, by the way, in the physical string literature. I mean, I think they invented this, what in physics is called conformal gauge, these isothermal coordinates. But there, just a small remark, there is the last pages of the book Linear and Nonlinear Waves by Whitham.
Right.
There's a book on PDE. The last 2 pages of the book, I mean literally the last 2 or 3 pages of the book, are on this Born-Infeld equation. And it's also a nice reference where they, if you are not aware of it and you are interested in it, it may be nice to look at the 2 pages.
Yes, thanks. So this is the same theory, right? The Born-Infeld soliton theory is the same as time-like maximal surface theory. I mean, is that kind of? It is.
Yeah, I mean, it's the same. It's
the
same. Yeah. I mean, it's the same. Actually, funny. The history is they nowadays we would think of the Born-Infeld equation as a string or maximal time-like minimal surface equation in a particular gauge, but they wanted to solve the Born-Infeld equation, I think, and they said, well, this Born-Infeld equation is just string theory, which at that time was not really so well formulated. Anyway, it's very interesting to read the old papers by Barbashov and Chernikov. And although I cannot be fully responsible, or I don't get some part of your question, but basically I think it is, I mean, they are discussing the same problem.
Right, yes. Great. Any other questions? There are no chat box questions this time. Okay, then thanks a lot, Adam. I hope we can meet at some point. Sorry, it was all online and yeah, so, okay, thanks a lot. And we can now stop this Zoom meeting.